In this lesson, we're going to learn all about the graphs of the sine and cosine functions. The graphs of the sine and cosine are the first two examples of graphs that are periodic, meaning that they have a set pattern that repeats over and over to infinity. These particular graphs look like a wave pattern. So for instance, the graph of y equals sine of x looks like this. The graph of y equals cosine x looks like that. They're very similar to one another. A couple of small differences. If you'll notice, they both repeat between a maximum of 1 and a minimum of -1. And the pattern repeats itself in a distance of 2 pi. That happens for both cosine and for sine. But that pattern that repeats is slightly different depending on what you call your starting point. So the obvious starting point is 0. The sine is 0 at an angle measure of 0, but the cosine is 1 at an angle measure of 0. So you have a slightly different pattern in that respect. But in general, they do look extremely similar to one another. They have important properties, such as the domain and the range, but then they also have what we call the period and the amplitude. The domain of the sine function is all real numbers. You can put any number that you want into the sine function, that is any angle measure that you want, and you're going to get something back out. You're not going to get undefined or, division by 0, square roots and negatives. It's not going to happen with the sine function. But the range is very much restricted. The range is only from -1 to +1 if you don't include any changes to the graph. The period is defined as how long it takes for the graph to repeat itself. The standard period for sine is 2 pi, because after an angle measure of 2 pi, you start seeing the same pattern over and over again. So you start with this pattern right here. Once you get to 2 pi, it repeats, and you see the same pattern again until you get to 4 pi. So every 2 pi, the pattern repeats itself. So that's what is known as the period. And then the amplitude is the maximum distance from the axis that you're bounding between. So this axis in this case would be the x-axis. The amplitude is the maximum distance from the x-axis in this case, which is 1. The same thing for cosine. It has these same sorts of properties. Domain and range, which we describe for all functions. The domain of cosine is -infinity to +infinity. Again, there's no number that you can put into the cosine function and result in division by 0. The range also is -1 to +1, because it doesn't go anywhere above 1 or below -1. The period, the amount of time it takes for the pattern to repeat, is 2 pi, just like in sine. And in this case, the amplitude, the maximum distance from that center point, is 1. And this is all without any sort of rotation or any sort of transformations occurring, so keep that in mind. Now, where does the graph shape come from? Where does it get this wave pattern? We know that sine and cosine are inherently related to circles, but why do we get the shape of a wave pattern when we graph sine and cosine? So I've got a couple of applets I'm going to show you to help you understand where this comes from. So let's get looking at those. Let's begin with the derivation of the graph of sine. So these are all based off of circles, okay? And so I've got a circle, and the radius here is 1. I didn't put it on an axis or anything because I don't want to. I've want it to be centered at the origin, but I didn't want it to overlap the graph I'm drawing. So this is a unit circle. So it's a circle of radius 1. And I have point P on my circle. And what's going to happen is, as I move point P, it's going to plot on the axis to the right the y-coordinate of point P. So what's important about the y-coordinate of point P is that we know the sine of some angle measure is equal to the y-coordinate off of a unit circle. The cosine of an angle measure is equal to the x-coordinate off of a unit circle. So I basically set this up to where I'm getting P is the coordinates of a point on the unit circle, and you can see those coordinates here for x and y. The angle measure for P, standard angle measure from the horizontal, is given in radians and degrees. And then up here, you're given the sine of that angle measure, which is just the y-coordinate. So you can kind of reference along with that. So here's what I'm going to do. I'm going to rotate point P around the circle. So as I move point P around the circle, this is where I start getting that wave pattern. So as I get up to pi over 2, which is an angle measure of 90 degrees, I'm at the y values are as large as they're going to get off of the unit circle. So I maximize those. And then the y values start decreasing from that point. And they decrease until they get to 0, and that's at a measure of pi. And as you continue rotating, they're decreasing further until they get to the minimum y value on the unit circle, which is at 270 degrees, or 3 pi over 2 radians, and that's at -1. You keep rotating around, and you complete that pattern of the wave that's drawn out here at 2 pi. And if you continue on around, it doesn't really, this applet doesn't really take into account larger angle measures than 2 pi. It's just going to redraw the same points over and over. But you can be assured, if you press the show graph button, that this will give you the graph of sine. And it does go on in both directions toward infinity, repeating the exact same pattern. So that's where the graph of sine comes from. The graph of cosine is essentially the same. You can use the same sort of setup, and that's what I have. The only difference is, for the graph of cosine, I'm taking the x-coordinate of point P and I'm plotting that. So initially, point P is at x equals 1 and y equals 0. So the y-coordinate the x-coordinate of point P is what we've plotted here, which is at 1. And this is our angle measure theta along this axis. So theta is 0 and x is 1. That's why I'm up here. And as theta increases, the angle measure increases, well, the x-coordinate on my circle decreases to a point where the x-coordinate gets to 0 by pi over 2. As the angle measure continues to increase, because now, if you think about the angle, here's theta, it's increasing. Whoops. Well, I'm trying to just grab the point there. It won't let me. The angle measure is increasing, and it continues to increase all the way around the circle. But as we get to 180 degrees, now the x value is as small as it's going to get, which is at -1. And then if you continue rotating, you get down to 270 degrees where you're back at 0, and on around to 2 pi, where you're back to where x is equal to 1. So that's where the graph of cosine is coming from. And if you show the graph of cosine, this black line shows you that it's mapping out exactly what you would expect, and it is continuing on in both directions toward infinity. So that's where the graphs of sine and cosine come from. Now let's take a look at the different transformations of sine and cosine. So the transformations of the functions sine and cosine can be wrapped up in these formulas right here. So y equals c plus a sine, in parentheses, b times the quantity x minus d. And similarly, y equals c plus a cosine, then in parentheses, b times the quantity x minus d. Which may look confusing at first, but we'll talk about all the different changes and how they work out. So, just like all functions we have studied so far, the trigonometric functions have basic transformations that affect what their graphs look like. These transformations are slightly different from the functions we've studied so far because of their periodic nature. They're transformations that affect the trigonometric graphs are the value a, which is the amplitude, so the number multiplying sine or cosine. This is the maximum and minimum height of the graph. B is the period, and that's how long it takes for the wave pattern to repeat. C is the vertical shift, so just moving the graph up or down a certain number of units. And D is the phase shift, which is the same thing as a horizontal shift. It's just named a phase shift when it comes to trigonometric functions. So starting with amplitude, for the graphs of sine and cosine, amplitude is the maximum and minimum height that the graphs reach. The standard graphs have an amplitude of 1, but the amplitude is determined by the value multiplying the function. So in the functions y equals a sine x and y equals a cosine x, the amplitude is determined by the constant absolute value of a. If the amplitude is negative, the function gets flipped vertically. But the amplitude itself is measured by an absolute value. The period of a sine or cosine function is the amount of time it takes before the wave pattern repeats itself. If no changes are applied, the default period is 2 pi. In the functions y equals sine bx and y equals cosine bx, so the constant is multiplying the angle measure now and not the function itself, the period is given by 2 pi divided by the absolute value of b. So the original period is 2 pi. If we divide 2 pi by the constant b, the absolute value of b, then we're going to find out, the number of patterns that repeat basically within 2 pi, a distance of 2 pi. That'll make more sense when we do some examples. The phase shift, this is the amount of time, the amount that the graph is shifted to the left or right. So remember, this always goes in the opposite direction of the sign within the function. So the graphs of y equals sine x minus d and cosine x minus d is shifted to the right or left by d units. The only thing that's different about this is this number is affected by a period change. So you have to factor out the change in period first so that you can work with these independently. The vertical shift is the amount the graph is translated up or down, and the graphs of y equals c plus sine x and c plus cosine x are just shifted up or down by c units. So whatever that number is how far up or down the graph is shifted. So putting it all together, the functions that we saw earlier, y equals c plus a sine b times the quantity x minus d, and y equals c plus a cosine b times the quantity x minus d, make up all the different transformations that can occur. One thing to make sure of is that there's no set of inner parentheses. I'm sorry, that if there is no inner set of parentheses, you need to factor out the value b so that you get the correct phase shift on your graph. So let's take a look at a couple of applets which describe the transformations of sine and cosine. Let's get started there. So transformations of the graph of sine. So notice I have it written as c plus a sine, then in parentheses b times the quantity x minus d. I have sliders here which can affect a, b, c, and d, so each of those constants. A is the amplitude, b is the period, c is the vertical shift, and d is the phase shift. And then over here, very rudimentally, it's going to describe the function that would create that graph. I didn't program it to do any sort of like simplification, so 0 plus 1 times sine, like you wouldn't write it this way, but I just made it so that you could at least see what's happening with the function. And then I have a button up here which allows us to show the original graph after we make some changes so that we can kind of compare the differences. All right, so let's start with individual changes at a time. So amplitude. Amplitude's pretty easy once you see it. So if I change the amplitude to 2, then what that means, or something close to 2, there we go. What that means is it's the maximum and minimum value that the graph's going to reach. And this is based off of a central axis, so it's not necessarily, it's always going to be positive 2 and negative 2 if your amplitude is 2. If your central axis is shifted upward, then it could be like between -1 and 3, for instance. It's just the maximum distance from a central axis. All right, and if you further increase it, all the way up to, say about 4, then, the amplitude is just the maximum distance from that central axis. If you decrease it down to 0, then of course you get a line because it's 0 times your function, cancels everything out. If you make it negative, then our graph is just flipped upside down. So if we show the original graph here, then you'll see that the graph is actually flipped upside down when we have a negative amplitude. We generally consider the amplitude as a positive value, but you can think of it in terms of as a vertical flip as well if you include it as a negative. Okay, so now let's look at what happens with the period changes. So let me get back to the original. So right now my period is 1. So that means I'm going to have one full cycle that occurs within 2 pi. So if I change my period to 2, that means that I will have 2 full cycles occurring in a distance of 2 pi. So from 0 over here to 2 pi, I now have 2 full cycles. So this is one cycle here up to pi, and then a second cycle here to 2 pi. So that's 2 full cycles. That's what the period is measuring, the number of cycles that occur in 2 pi units. If I show the original graph, you'll notice that this wave pattern is repeating at about twice the amount of time, or about half the amount of time as the original graph. Okay, if I change that up to 3, then what you would imagine occurs. It just makes it so that you have 3 full rotations happening by the time you get to 2 pi. And I'm not quite at 3, but There you go. So you get the idea here. So this is one full pattern here, a second full pattern here, and the third full pattern there. So from 0 to 2 pi, in that case, 3 patterns occur. If you bring your value of b down to, say, a half, then only half of the pattern happens between 0 and 2 pi. So I haven't even reached a full cycle. And I won't reach a full cycle until I get over here at 4 pi, which isn't even on my scale. And if you kind of show the original graph there, you can tell, you know, I've only done basically this portion right here by the time I got to 2 pi. So only half of the cycle has been completed. Okay, so that's how the period works. Let me get back to the original here. The vertical shift is probably the easiest one. You know, it just is going to move the graph. Whoops, I clicked the wrong one. Up or down, depending if you have a positive or negative value. So the vertical shift, as I mentioned, the amplitude isn't always how far away, what the minimum and maximum value is. It's the minimum and maximum value from a vertical axis. So you can kind of imagine here a vertical axis that you're bounding between. The maximum distance from that vertical axis in this case is 1 or -1 this direction. If you change the amplitude to 2, it's just still just the maximum distance from that vertical axis. So that's what I meant when I talked about that earlier. And let's go back to amplitude 1. And so you can go up or down. So vertical shift is very straightforward either way. But notice it is just the number added in the front. Okay, and let's go back to the original. Phase shift. Phase shift is essentially just as easy. It's just a shift to the left or right. Oops. If I move my phase shift to 1.57, which is approximately pi over 2, I've just, now my starting point for the standard wave is just pi over 2 units away from 0, that is. So I've just shifted the thing to the right, in this case, by pi over 2. But notice in the formula, it would look like x minus pi over 2 would be a shift to the right. Okay? You can go further. If you go all the way to 2 pi, you basically get the exact same graph that you started with, because everything's just shifted that direction by, you know, the 2 pi, which is where your wave pattern began in the first place. You can go negative with it. You can shift to the left. Same thing happens. Now, the things start to get more interesting when you have multiple changes occurring at the same time. So, like for instance, let's say we have a vertical shift of 1, oops, and a phase shift of pi over 2, and an amplitude change of 2. Okay, so everything's shifted up 1 unit, so my vertical axis is up here at 1. Amplitude is 2, so the maximum distance from the central axis is 2. And I have a phase shift, which means, you know, my starting point right here is moved over pi over 2 units. Likewise, if I had a period change as well, you know, if the period was 2, for instance, then I would need to make sure I completed 2 full cycles by the time I got to 2 pi more than what my phase shift is. So things can get complicated, but at least if you use the formula the way it's presented here, with the phase shift, the period change factored out, these things work independently, and it makes things a little bit easier. Now, for cosine, it's basically the same. It's just simply you're working with, the wave pattern. Now, with cosine, it's basically the same. You're just looking at the wave pattern starting from a different point. So cosine starts at a maximum of 1, whereas sine begins its pattern at 0. The transformations are all the same. They affect it the same way. It's like if you had an amplitude of 3 and a vertical shift of, say, -1. Oops. There we go. Perfect. Then you have the vertical axis that you're, changing about is just shifted down 1. The maximum distance from that vertical axis is your amplitude, which is 3 units. So I'm bounding between a maximum of +2 and a minimum of -4, which is 3 units away from -1 in both directions. If I had a period change, then the period change, let's say it's 3, then I would be completing 3 full cycles in the amount of time it should take me to complete in the amount of time that it should take me to complete 1 cycle. The phase shift, which I thought I had at 0, but apparently not, works in the exact same way as well. It's just going to shift you to the left or to the right. The important thing is just to make sure, if you have a phase shift and a period change, that you have it written in this way where the period is factored out of the phase shift, so that these things will work independently of one another. Okay? Let's look at a few examples that are similar to what you might experience in the homework. So for example, find the period and amplitude of the following functions. Starting with a, y equals 3 sine 1/2 x. So the 3 is an amplitude change because it's a multiplier on the trig function itself. And this is a period change because it's multiplying the angle measure. So to determine the difference in the amplitude and the period, the amplitude is just whatever that constant is. In this case, it's 3. The period is 2 pi divided by the value b that's presented. So in this case would be 4 pi. Part B, y equals -2 cosine 3x. So the amplitude different textbooks will treat this differently. My experience says that the amplitude is always defined as the absolute value, so the amplitude is 2. And in this case, there happens to be a vertical flip as well. If the homework system you're using tells you that +2 is wrong, then just put -2 in. It doesn't really make a lot of difference in the end. But this is just kind of how always I was taught about it. The period change here is 2 pi over the absolute value of the number multiplying x, or theta, whatever the case may be. So in this case, the period change is 2 pi over 3. For example, determine the amplitude, period, any vertical translation, and phase shift of the following functions. All right, y equals 2 sine 2x minus pi over 3. Now, because we need to identify the period change and the phase shift, we're going to have to factor out this constant 2 from inside these parentheses. Otherwise, we have these two items interacting with each other. And it's much easier if we factor that out and make it so that they are not interacting. It's easy to do. So 2 sine, what would you do to factor out a 2 from a set of parentheses? Well, just pull the 2 outside of the parentheses. Then 2x divided by 2 is just x. That's what we want. But then we have to do pi divided by 3 divided by 2. And you might have to come off to the side and work with some fractions, but you're going to get pi over 6. And now you're done. You don't have to do anything further. Now the period change and the phase shift are independent of one another. And you can check to make sure you have the right one by distributing the 2 back in, which of course will give you 2x minus pi over 3. So the amplitude is 2. The period is going to be 2 pi divided by 2, which is pi. The vertical shift is none, so it's not being shifted up or down any units. But the phase shift, which is the horizontal shift, it's pi over 6 units, but you need to indicate whether you're going to the left or to the right. And just remember, it's the opposite of the sign that's in the function. So since it's x minus pi over 6, that's which is a negative direction, it's going to move me to the right. So it's just the opposite direction of the sign. Okay, this next one, y equals 1 plus 3 cosine pi over 6 times x plus 1/2. I've chosen this notation because sometimes the homework will do this to you, where this pi over 6 is the value of b, even though they're not putting a second set of parentheses around it. That's okay. That happens. It's pretty standard. The amplitude here is just the number multiplying the trig function, so that's 3. The period is going to be 2 pi divided by b, which is pi over 6. And it's already factored out. The way it's written, it's already factored out. So I don't have to do that part. Working with fractions here, so let's see, it would be 2 pi over 1 times 6 over pi. The pi's cancel out. So the period is 12. A way of thinking about this is, the way I've been saying it before is like, it takes, like if the period change was 2, then you would have 2 cycles completed by the time you got to 2 pi. Another way you can think of it is, in pi units, that's how long it takes to complete 1 cycle. So another way of thinking of this would be like, in 12 units, that's how long it will take to complete 1 cycle. Because if you think about it the way I've been saying it, it would be a little bit strange. You would complete pi over 6 cycles in 12 units, which kind of is strange. So it would take 12 units in order to complete a full cycle. The vertical shift. So the vertical shift is a number added to the function, which is 1, and it's going to go up because it's a positive number. And then the phase shift this is 1/2 of a unit, because it's the number added to x, and it's shifting, so you have to decide between shifting left or right. It's the opposite direction of the sign provided. So since it's a positive 1/2, it's going to be shifting 1/2 unit to the left. Now let's graph a few functions. So let's graph the function y equals -4 plus 2 sine x. In order to graph it, we have to determine, what's happening with all the different changes. So for instance, looks to me, well, let's just list them out. So we could have an amplitude change, a period change, a vertical shift, and a phase shift. So let's just list all of them that are occurring in this case. So the amplitude is the number multiplying my function. So my amplitude is 2. The period is the number multiplying x. Well, that's not happening. So the period is still 2 pi. So 2 pi divided by 1 in this case, basically. So it'll complete one full cycle in 2 pi units. The vertical shift is down 4 units. And there is no phase shift. Okay. So let's draw the graph based off of that. So I'll start with the vertical shift, because that's going to be my horizontal axis that I am, doing the wave pattern around. So it's shifted down 4 units. So I'm just going to draw it in as a dashed line, because it's not actually part of the graph. I'm just using it as a reference. So it's down 4 units. The amplitude is 2. So that means the distance from that axis is 2 units. So there's 2 units this way and 2 units that way. So that's my maximum distance away from that. Period is 2 pi, and I have no phase shift. So that means I'm going to start my original pattern at 0. In the original pattern for sine, you start at 0, which means the horizontal axis, basically. And then by the time you get to pi over 2, you're a maximum distance away. So by pi over 2, I'm going to be at positive 2. At pi, I'm back to my horizontal axis. Then at 3 pi over 2, I'm the maximum distance away again. And by 2 pi, I've completed my cycle. So this wave pattern is going to look like that. Sometimes you're only asked to graph one cycle. Sometimes you're asked to continue the cycle. Usually for most instructors, if you're just turning it in, one cycle is fine. But it's generally easy enough then to just repeat the pattern. So if I were to repeat the pattern, just kind of mark off where the maximum and minimum points occur, and then just fill in the wave in between. Okay. Oh, and I suppose I did that a little too fast. That shouldn't have been right exactly there. So back at 0 here. So there we go. Okay, so there's my graph. Okay, the next example is to graph the function y equals -6 cosine 2x. So the things that I want to do first off are identify the different changes that are occurring. So I notice that I have an amplitude change. And the reason I know I have an amplitude change is because I have this multiplier of -6 on my trig function. So that means my amplitude is going to be 6, but because it's negative, I need to make sure to remember to flip the graph in the end. Next is going to be a change in period. So normally, the graph of cosine completes its full cycle in 2 pi, from 0 to 2 pi, that is. But because there's a multiplier on my x, it's going to cycle through faster. So 2 pi divided by 2 tells me that the cycle is going to complete by pi. All right, now in terms of vertical shift or a phase shift, I don't have either one of these. The reason that I know I don't have a vertical shift is because there's no values added or subtracted to the function. So that doesn't exist. And then the phase shift, I don't have one of those because I would need something added or subtracted to the variable x. Okay, so if I had just wanted to graph the function 6 cosine of x. All right, so the only thing that I'm affecting here is the amplitude. Cosine starts off at its maximum and it ends at its maximum. So over here by 2 pi, I'm back at 6. Halfway along that interval, I'm at a minimum at pi. And then halfway in between those, I'm at 0. So I go from my maximum down to 0, down to my minimum, back up to 0, and back up to the maximum. And that gives the wave of cosine. Now, there are other changes occurring here. Number one is my graph is flipped. So all of these points are actually upside down. Okay, so I'm going to start at my minimum of -6, go up to 0, then up to +6, down to 0, and finally complete by 2 pi. But that's not the only change. I also have this change in period. So I need to complete this entire cycle by pi, which means I'm still going to start at -6 for 0. But I need to be back at -6 by pi. So halfway in between that interval, I've got to be up at my maximum. So that is, in this case, pi over 2. I would be at my maximum. And then I'm going to be at 0 at pi over 4 and 3 pi over 4. And a way you could tell that for sure, if you're not quite sure exactly how I'm going about this, you could kind of sketch it out. You know that cosine, its points of interest are 0, pi over 2, pi, 3 pi over 2, and 2 pi. All right, so I need to be at my maximum, then I'm at 0, then I'm down at my minimum here, then I'm at 0, and then my maximum. So if I need to complete this cycle by pi, I basically divide each one of these by 2. So 0 divided by 2 is 0. 2 pi over 2 is pi. So that means I've finished that cycle by pi. This one's an easy one. It's just pi divided by 2, so pi over 2. And pi over 2, if I divide that by 2, then I have to work a little bit with fractions. Invert and multiply, so this is going to be pi over 2 times 1/2, which is pi over 4. So this value is pi over 4, and this one likewise would be 3 pi over 4. Exactly what I have. I just sort of did it from points rather than from, writing out the actual values. Either way that works for you is fine, of course. The last thing you would need to make sure of is that you include the flip. So anywhere you had a maximum, that would need to flip and be a minimum. And anywhere you had a minimum, that would flip and need to be at a maximum. So just kind of keep that in mind as well. But once that's all put together, I now have a decent sketch of my curve, and that is one cycle. If I needed more cycles, I could easily extend the graph and get more. That's not a problem. Graph the function y equals -4 plus 3 times the quantity x plus pi over 4. So let's begin by starting to identify the different changes that are occurring. So clearly there is a vertical shift that's going to go down 4 units. So normally the axis that I'm kind of doing this wave pattern around is at the x-axis. Now that's going to get shifted down 4 units. So I'm just going to draw a dashed line that's right here, just to give me a reference. The amplitude is 3. So that means from that axis, I'm going to go a maximum distance of 3 units away. So that would be to here, that would be positive 3 units, and down here, which would be negative 3 units. So I'm going to bounce between -1 and -8, or -7, it looks like. There is no difference in phase shift. I'm sorry, in period. So the period is still 2 pi, but there is a phase shift. And that phase shift, what it's going to do is it's going to move everything to the left by pi/4 units. So normally the wave pattern of sine begins at the horizontal axis and right at the y-axis. So normally I would start the wave pattern right here. But since it's being shifted back pi/4, I need to find out where I'm going to be starting now. So this unit is pi, so that means halfway in between would be pi/2. So that would be pi/4 right here. So I'm going to indicate that. So this is negative pi/4. So that's where my wave pattern is going to begin. Now, it's going to have to, the wave pattern is going to have to complete by the time I get, 2 pi units away from that. So if I take negative pi/4 plus 2 pi, that should tell me where my wave pattern is going to end. So I need a common denominator, so negative pi/4 plus 8 pi/4 is going to be 7 pi/4. Or another way of looking at it is pi/4 units to the left of 2 pi. So right here, this is my 7 pi/4. That's where my wave pattern is going to end. Which means at that point, I'm going to have to be back to, my starting. Now I just kind of have to fill in what's happening in between. So the graph of sine goes up and reaches its maximum, usually by pi/2. So let's kind of sketch this out as to what this is going to look like. So let's do this. Let's say sine begins at 0, which is the horizontal axis, goes up to its maximum, and then it goes back down to 0, then down to its minimum, and then back to 0. So the normal function, sine x, this occurs theta equals 0, then pi/2, and then pi, 3 pi/2, and 2 pi. Now everything here is going to be shifted to the left by pi/4. So what happens when I take sine of x plus pi/4 is that all of these points get moved back pi/4 units. So 0 minus pi/4 is negative pi/4. 2 pi minus pi/4 is 7 pi/4. We just kind of have to fill out the rest of these. Pi/2 minus pi/4 is going to be pi/4. Pi minus pi/4, you can check with your fractions, but it's going to be 3 pi/4. And then 3 pi/2 minus pi/4 is going to be 5 pi/4. So we just kind of need to know where these points are. And on my graph, this would be pi over 4. This would be 3 pi over 4. And this would be 5 pi over 4. Now, at negative pi over 4, I'm at 0, my horizontal axis. At pi over 4, I'm at my maximum. So that means at pi over 4, I'm 3 units away from that horizontal axis. 3 pi over 4, I'm back at 0 again. So right here. Then at 5 pi over 4, I'm at a minimum, so I'm 3 units below that horizontal axis. And then at 7 pi over 4, I'm back to the horizontal axis again. So my sine wave, in this case, looks like this. And as I mentioned, generally if you can draw one section of it, that's all instructors are ever really looking for. Because if you can draw one section, you can easily repeat that pattern forever. So what I tend to just have students do is just kind of put arrows on the end of it like that, indicating that it is continuing on. So what I'd like to do now is help you work through a problem in your homework, just so that you can see exactly how to input your answers here. So here's an example problem where we're asked to graph y equals negative 4 cosine the quantity 2x minus pi over 2. So in order to do that, it's definitely going to be helpful to enlarge the graph here that's presented. But we're going to need let me get some Scratch. So now I'd like to show you how to graph these functions in your homework system. So I've pulled up a problem which has given me y equals negative 4 cosine of the quantity 2x minus pi over 2. And it's given me a graph that's already scaled a little bit in order to put my graph here. So let me click to enlarge that so we can see it a little bit better. Now if you'll notice, there's already some different tools here that will let you draw with. So there is this tool here, which is a wave pattern. Notice that it's starting at its minimum, that horizontal axis, then going up to its maximum. So this is the sine wave, and then right next to it, this is the cosine wave. So they're giving you some tools to draw the waves with those. Now, before we go to put that on the graph, what we should do is first kind of identify the changes that are occurring. So we have y equals negative 4 cosine of 2x minus pi over 2. Now, the first thing that I need to do is factor out the 2 from the x so that my phase shift and my period change are not affecting one another. So I'll write this as 2 times the quantity x minus pi over 4. All right. Now, that shows me that my amplitude is 4, but we have a vertical flip because it's negative. And then my phase shift is pi over 4 units to the right. There is no vertical shift, but there's a period change. So the period normally is 2 pi, but since this multiplier of 2 exists, I divide that by 2, so my period here is pi. Okay, now I'm working with the graph of cosine, so over here on my graph I'm going to choose the cosine tool. And what I do then is just click on the graph, and it just puts the function there. And what it has you do is, in some problems it'll actually have you type in what the amplitude and the period are. In some problems like this one, you have a slider. So it just kind of depends on the individual problem. So the amplitude, this button here, starts off at 1, and you can slide it to whatever changes you need. So our new amplitude is 4, I'm sorry, not 3. So we'll slide that up to 4. Alright, so that's a good start. Now the period is pi. So I'm going to take my period and I'm going to slide it back to pi. And if you'll notice, this is very straightforward because the graph kind of changes with you. So when you make these. We did not have a vertical shift, so I'm going to leave that as 0. But we do have a phase shift, and this phase shift is pi over 4 units to the right. So you can calculate what pi over 4 is by approximating on your calculator, but you can actually just type in pi over 4, and it'll know what to do with that. So it'll make that change accordingly. Now, lastly, I have this vertical flip. So the vertical flip exists because my amplitude was negative, which means I have a y-axis reflection. And if you click the y-axis reflection button, it will update and make that change. So let's close that out now and hit save, and it'll save my graph. And then when I hit check answer, it'll tell me if I'm correct or incorrect. Now, the one thing that I want you to make sure of, when you go to do your paper exams for this class, you're going to have to actually draw these curves. They're not going to just be drawn for you on the computer. So one thing that you should probably do is when you're making these changes over here is to sketch them out for yourself. So exactly how we were doing in the example problems earlier in the video. So for instance, there's no vertical shift. So I have this horizontal axis right here at 0. And then the amplitude is positive and negative 4. So 1, 2, 3, 4, that's my maximum. 1, 2, 3, 4, that's my minimum. And the units, I generally would put pi and 2 pi in each direction just to kind of start off with. Oops, I meant to put pi there, sorry. So negative pi and negative 2 pi. So this would be negative 3 pi over 2, negative pi over 2, and so forth. Now to fill in the rest of the graph, and I just extended my paper so I could get some space to write, what you could do then is, think about how cosine works. All right, so the function cosine of x, normally when you're at 0, it's at a maximum. And then when you're at pi over 2, you're back to 0. At pi, you're down at a minimum. And 3 pi over 2, you're back at 0. And 2 pi, you're back at a maximum. The way I'm filling this in is, just from the standard curve of cosine. So negative 1, positive 1. I'll call this pi, 2 pi. So this would be pi over 2 and 3 pi over 2. Starts at 1, comes down to 0, then goes down to its minimum, which is negative 1, back to 0, and up here. So I'm just kind of following this standard wave for cosine. Now, when I put a period change and I put a phase shift in here, things are different. So what I'm going to do is I'm going to first apply, it doesn't really matter which one you do, I'm going to first apply my period change, which makes it so everything happens by pi. So not only does the 2 pi get divided by 2, but all the other points do as well. So I have 0, pi over 4, pi over 2, 3 pi over 4, and pi. So my wave has to kind of finish in those units instead. Now it's going to be shifted to the right. So cosine 2 times x minus pi over 4. So all these points are just going back, going forward, to the right by pi over 4 units. So 0 plus pi over 4 is pi over 4. Pi over 4 plus pi over 4 is pi over 2. Pi over 2 plus pi over 4 is 3 pi over 4. 3 pi over 4 plus pi over 4 is, I'm sorry, not 2 pi, just pi. And then 5 pi over 4. And you can just work with the fractions if you're uncertain, you know, that's the way that happens, but that is certainly the way those work out. Then the last change we have to take into consideration is the vertical flip. So basically, if you're flipping everything vertically, then at pi over 4, where you should be at your maximum, you're actually going to be at your minimum, because that's just flipped vertically. Pi over 2, you'd still be at 0. 3 pi over 4, you would now be at your maximum. Pi, you would be at 0, and 5 pi over 4, you would now be at your minimum. So everything just flips vertically. So putting this together on the chart here, pi over 4, so if this point here is, I have pi marked, this point here would be pi over 2, so halfway in between those are my pi's over 4. So pi over 4, I'm supposed to be at my minimum, so at negative 4. Then by pi over 2, I'm at 0. Then at 3 pi over 4, I'm up at my maximum, which is at positive 4. And then by pi, I'm back down to 0. And by 5 pi over 4, I'm back down to my minimum again. So my curve is going to look something like this. And you want to make sure you have this skill in order to draw these functions on paper, because when you take the paper and pencil exams, unfortunately you don't have the computer there like drawing in the changes as you are, you know, inputting them. So you need to be able to identify the changes and draw them. So keep that in mind. Now let's just compare this back with what we had originally. So looking back to the graph that we have on the computer screen, it looks basically the same. You know, here's my minimum point and maximum points at 4 and negative 4 respectively, so that's correct. We have the graph coming back to pi over, going through the x-axis at pi over 2 and at pi, so those are correct. And it looks like we're graphing it onto 5 pi over 4. They've kind of started the cycle back at 0. But if you continue our cycle, we would be back to 0 if we went pi over 4 more to the left. So our cycle matches up their cycle as well.